And we'll move on to Houjun Tang's presentation about earthquake simulation and their usage of HDF5.
Hello again. Okay, I will be talking about efficient I/O and data management, basically integrating HDF5 into Exascale earthquake simulation project. And this is ECP application development project called EQSIM. It is a framework for regional scale fault to structure simulation. And here in this slide shows the basic workflow. So basically, we simulate a regional scale earthquake event. We usually do a San Francisco Bay Area. Domain is about 80 kilometers by 120 kilometers. And then with the simulation, we generate the Earth's ground motions and then record those motions into a file. And then those output ground motion time series data will be used for infrastructure response simulation analysis. So basically, we put buildings at different locations in the simulation domain and assess their damage corresponding to an earthquake event. And then we plot infrastructure demand or risk map to show where is the damage is mostly happening, and people should be cautious in those areas, and the buildings in those areas should also be strengthened. So for the EQSIM project, or integrating HDF into this project, there are some basic needs. So basically, we are moving into the exascale simulation, and there are many requirements for both I/O and data management. So there is a big increase in the volume of both input and output data, and that it could significantly affect the overall simulation time. And there are new requirements, and also for multidisciplinary team for this project, we have earthquake engineers, mathematicians, and other scientists that may want to access the simulation data, and to provide easy access data format, and for efficient analysis and data sharing is also important. And we also require new techniques such as compression is definitely needed to enable a large-scale data output and analysis. And with the HDF5, we believe we are meeting all of these requirements and goals, and I will go into the details. So for the current workflow, can be divided into different phases. First is the pre-runtime. The seismologist needs to determine or use what material model under the ground, and there's usually the surface geology, the elevation of each point in the problem domain, and then below the surface, what are the material properties of the rocks and other things. And then for that simulating the actual event, there will be like the rupture scenario. And currently, all of these input files have been converted into HDF5 from various previous formats, including text files and homegrown custom binary files. And translating them into a single file format greatly improves the data management, and also makes it very efficient to rate them in parallel, especially in very large-scale simulations. And during the ground simulation, the simulation code we use is called SW4, and is seismic wave force order. So it will generate the ground motion time history data and then output to a HDF5 file. And the motion data can be a single grid point, which corresponds to a ground location. And people also need like more than a single point, is more for a sub-volume or 3D volume of the domain. And those have all been also converted into using HDF5 for storage. And then once those data are generated, and then the structural engineers will use the motions and run simulation and analysis, visualizations, and with those data to provide the final output. So first, a little bit more details about the material model. So previously, we used the custom binary format, or R file, and then there are some additional requirements, and we come up with this new SQL format, and it is stored in HDF5, which enables it to be easily visualized for people to just plot images like this to cross sections. And it also allows converting the existing material model to the new format with HDF5. And there's also some other work to based on some actual observation data to inverse the material properties and then save it to this SQL format. And then for the rupture scenario, so previously the rupture data was stored as a HUSky2 text format called SRF. It is extremely slow to read at a large scale. So we have done simulations on the Summit supercomputer with 922 nodes and 3,600 nodes. And using the previous ASCII2 text format, it would take hours or more to read a text file into other processes. But after we converted to use HDF5, it just takes seconds to minutes. And also with the HDF5 format, it is easy to visualize with different language, Python, MATLAB, R, etc. And next, moving to the outputs. So for outputs in this project, we have two types of analysis. One is called weak coupling analysis, and the other is called strong coupling. So weak coupling basically takes one grid points time history data and then put it as the base of a building and then performs the building analysis. And the strong coupling is take a 3D subdomain and then put that with steps and then simulate it with a building. So for the single point station time history, we have the output called the SEC HDF5. So SEC is a pre-existing format that is a binary, but the problem with the SEC format is each station results in one file, and in a typical large-scale simulation, there can be like 3,000, 5,000 stations, and resulting in tens of thousands of files, which is extremely difficult to manage. So then we come up with the corresponding HDF5 format, such that we have only one single HDF5 file, but we have a number of groups corresponding to those stations, and also the data sets corresponding to the XYZ direction components. So the SEC HDF5 format also allows downsampling. So usually the simulation time stepping is very fine-grained, and the analysis may not need that small time gap. So then we can do the time downsampling and make the resulting data smaller, but still useful. And we have some I/O time comparisons, so we can see the HDF5 implementation offers much better performance on both Quarry and on Summit. And then next is a weak coupling of the time history data. So this is directly using the SEC HDF5 output and put building on top of that for earthquake event analysis. See if I can play this video. I guess not. Well, so the gist is that we can put buildings with the time history coming from the simulation and then assess the danger of the building corresponds to an earthquake event. So there are some standards for accessing the damage. So we can calculate the drift of the roof and the ground of a story in a building, and then if it exceeds 2.5%, we consider it is a permanent damage to the building. And then based on this information, we can plot the risk map across the simulation domain. Next is the strong coupling. So strong coupling is using a 3D subvolume of the time history, consisting of a large number of grid points, and then put put a building into that subdomain and see what happens. So previously, we were only able to output a select subdomain. If you see on the top left figure, the gray boxes inside this domain, due to the large size of the computation domain. So the recent large run on Summit, we have 400 billion grid points in total. So even just saving the top surface up to certain depths is taking a lot of space, and in many cases it is impossible to store that amount of data. So compression comes into rescue for us, and currently we have explored a compression library called ZFP. We are using a lossy compression since we have found that the lossy, even if it is lossy compression, the accuracy is still acceptable in the main use cases. One is for the building analysis, and now the other one is for plotting the surface motion data. So on the right-hand side, this is one simulation run we have. Hypothetically, if there is no compression, for outputting the entire domain up to 150 meter steps, it will take about 76 terabytes. So we actually don't have that much space in our allocation on the supercomputers. So it is basically impractical to output this amount of data. However, with the CFP compression, we have tested with two compression accuracies. One is the lossy compression is really bring down the total size. So we do have an incredible compression ratio. So using the accuracy of 0.01, we get 261 times smaller data. So 76 terabytes to 293 gigabytes. And if we want to be even more aggressive, then we bring down the accuracy to 0.1, then we get even higher compression ratio up to 494, and that results to just 155 gigabytes. And also another convenient thing with HDF5 is that even after using this compression, the HDF5 still appears the same. And for people just to want to access the data, for example, in Python, they can just install a Python package called HDF5 plugin, and that will allows the HDF5 to transparently read the compressed data without any user intervention. So in Python script, you just import this module and then open the file as normal and do the data selection and access as normal, and it is how the compression is completely transparent. So see, yeah, this movie may play out. So this is one of the scenarios where we have the ground motion across the compute domain, and we see the waves propagating through. In the middle is the fault, and it goes around the area. So in summary, so the integration of HDF5 into the EQSIM project have greatly improved the efficiency and for the data generation, processing, analyze, and visualization. So the self-describing format is good to use, and it has the Python or MATLAB interfaces allows scientists from different domains using their favorite programming language to access the data and process them. And we have improved I/O performance of both input and output. And we have using HDF5 as a file container reduces the number of files from thousands to just one per simulation. And then the transparent compression capability allows saving and analyzing more data pain-free. So that concludes my presentation, and any questions?
Thank you, Tom. Any questions? Right. Oh, Lee?
So for the Python visualization, how do you load the 260 gig file?
Oh, so usually the analysis, they do not load the entire data. So we as you see the top left figure. So we save the entire domain, but usually the analysis is on these gray boxes. So the read just reads a small, very small subdomain. Because otherwise, if the reader wants the entire domain, the data has to be compressed, decompressed, and 155 gigabytes goes back to the 76 terabytes, which I don't think any computer will hold.
And yeah, there is a hand raising.
Yeah, Houjun, very interesting talk. I have a very similar data situation as you that also has benefited from using HDF5 and also ZFP. My question is, those compression ratios are incredible. Two questions: is your native data format 64-bit? And second, do you have a lot of constant values or zeros in there? Because even when I compress my data pretty aggressively, I get about 20-to-1 compression ratios.
Yes, the data is 64-bit double values. And for zero values, at the beginning of the simulation, there are, if you see the bottom middle figure, at the beginning simulation data are usually 0. And so this figure is near the fault, so the zero value is much less, but further from the fault, there are much more zero values.
So is that why you think you're getting such good compression ratios?
Yeah, I think so.
Okay.